So now we're going to take a look at an example of a function, and we want to use algebraic means to be able to evaluate all four of these things. We want to know what the critical points of this function are. We're going to find the absolute maximum and minimum values on a closed interval. We're also going to evaluate where the function is increasing or decreasing, and we're going to find the local mins and maxes. And we're going to do all this without graphing the function, and then we'll verify our work by graphing the function at the end. So let's start with critical points. So recall that a critical point is a place where our derivative is equal to 0 or our derivative does not exist. And in this case, we see that this is a polynomial. It's a continuous curvy squiggly function. We know that it's not going to have any cusps. It's not going to have any places where the derivative doesn't exist. So let's go ahead and take the derivative. It's pretty straightforward because we can use power rule. We see that the derivative of 3x to the fourth is 12x cubed minus 16 times 3 is 48, x squared, and 18 times 2 is 36x. So this is the derivative of our function, and we want to know when is the derivative equal to 0. That's the same thing as having a horizontal tangent line. Notice that there's a 12 in each of these terms, and there's also an x in each of these terms. So I'm going to go ahead and factor out 12x. So 12x is equal to, or when I factor it out, I get an x squared in the first term, because 12x times x squared is this x cubed term. 12 times 4 is 48, and x times x is x squared. And then 12 times 3 is 36. And that leaves me with that. So we're getting closer, but we still need to factor this polynomial. And it turns out, this is an easy polynomial to factor. That was somewhat intentional in the construction of this example. But even if this wasn't easy to factor, it's something that you could do with a quadratic formula. I know that my two terms need to multiply to be a positive 3, and they add together to be negative 4. So I'm going to go with two negative numbers, negative 1 and negative 3. And I can verify really quick that when I go ahead and multiply this out, I get x times x is x squared, x minus 3 minus 1 is negative 4, and negative 1 times negative 3 gives me the positive 3. So we've just factored this, and now that we've factored it, we can easily tell what each of the roots are. That this polynomial is going to be equal to 0 when x equals 0, when x equals 1, and when x equals 3. So these are my critical points. That was pretty easy. It means that we've completed number 1. Now we need to find the absolute maximums and mins on the closed interval closed interval from negative 1 to 4. There are a number of ways that we could do this. If we had already found, we could actually go through and evaluate whether they are local maxes and mins and get an idea of what the graph looks like. Instead of doing that, we're going to do it algebraically, and by that I mean we know that the maxes or mins have to be either endpoints or critical points. And so I'm going to evaluate, well, what is my function at each of these points? If I plug in negative 1, 4, 0, 1, and 3, those are the only possible inputs. They're either going to be maximum values or minimum values, or neither. And so I want to find which of those those 5 x values, which has the highest y value and which has the lowest y value. So let's just evaluate that. I'm looking at f of negative 1. That's going to be equal to 3 times negative 1 to the fourth minus 16 times negative 1 cubed plus 18 times negative 1 squared. And that's all equal to, let's see, negative 1 to the fourth becomes positive, so that's 3. Negative 1 cubed is negative, so this becomes a negative 1 times negative 16 is a positive 16, and negative 1 squared is positive is 18, and that's equal to, let's see if I can do this in my head, That would be 30 plus 4 plus 7. That's 37. You can always check me on the calculator to make sure that that's correct. And now let's do our next. I'm just going to go in value of x's. It doesn't matter what order I go in. I could do the endpoints first and the critical points next. But f of 0 is something easy. I can do it in my head. I can look at my original function. I see 0, 0, 0. So f of 0 is actually just equal to 0. Easy. F of 1, I'm going to write out. It's 3 times 1 to the 4th minus 16 times 1 cubed plus 18 times 1 squared. And that's all equal to 3 minus 16 plus 18. And so that's going to be equal to 5. That means when I plug an x value in, I get a height of 5. Going forward, there are only 2 more. F of 3. This is one that I can't do in my head. This is 3 times 3 to the 4th minus 16 times 3 cubed plus 18 times 3 squared. And finally, f of 4 is equal to 3 times 4 to the 4th minus 16 times 4 cubed plus 18 times 4 squared. And I'm going to bust out my calculator for those. It's fun for me to do mental math, but it's something that I can't do always in my head. So I get 3 times 3 to the 4th minus 16 times 3 to the 3rd plus 18 times 3 squared gives me negative 27. And finally, I get 3 times 4 to the 4th minus 16 times 4 to the 3rd plus 18 times 4 squared. That gives me a positive 32. So what did we just find? From this evaluation, we see, why was I plugging it into the original function and not the derivative function? It's because we want to know what is the height. We don't want to know what is the slope of the tangent line. So at each of these places, we have unique heights. And we see that which value is the smallest? F of 3 has the least height because it's down at negative 27. And f of negative 1 has the greatest height because it's up at positive 37. So we just found from this numerical analysis that on this closed interval, x equals negative 1 is the absolute max because it had the highest value, and x equals 3 is the absolute min because it has the lowest value, and both of these are on the interval from negative 1 to 4. From this also, we can get sort of a feel of some of what's going on in the graph as well, but we're not gonna dwell on this too much. Instead, we're going to move forward and we're going to look at where the function is increasing or decreasing. And to do that, I'm going to use some of the information that we already have. We already found the derivative, and we want to know when is this derivative positive and when is this derivative negative. And we know exactly the places where it's equal to 0, and we're going to break up the domain of our function based on these critical points. So for 3, we're finding when is our function increasing or decreasing. I'm going to do a number line because I like to visualize things in terms of a number line. We found that our critical points were at the point 0, 1, and 3. These are the places where our derivative was equal to 0. And that means that there's nowhere else on this graph that our derivative is equal to 0. And it means that our derivative must have the same sign all the way through, meaning if it's negative here, it's negative for every value along here. And if it's positive here, it would be positive for every value between here. Why doesn't it switch? Switching between negative and positive would mean that it would have to go through 0. This is actually, the reason is intermediate value theorem from our previous, so this is an application of that. So let's look at each of these intervals individually. Let's start by looking at the interval as x goes from negative infinity to 0. So on this part of the graph, we want to know, is the derivative positive or negative? And I'm going to do that. We could do it in a number of different ways, but the easiest way to do it is to evaluate if it's positive at any of these points, it would be positive everywhere. So I'm just going to pick an easy point. I'm going to write it in green. I'm going to pick the point, maybe I'll put it with a star, -1. This is just my check value. And I'm checking to see when I plug in -1 into my function, not my function, but my derivative, do I get a positive or a negative value? So I'm going to check what is f prime. Whoops, that shouldn't be there. Of -1. Sorry, this isn't meant to be confusing. I'm plugging it into my derivative. And what is my derivative function? Recall we found the derivative over here is equal to 12 times -1 cubed minus, you can't see any of this because I'm left-handed, 48 times -1 squared plus 36 times -1. Why are we plugging this into the derivative function? Because we want to know whether the derivative is positive or negative. Let's compute this. -1 to the third is negative, so I get -12 minus 48 minus 36. And really, I don't have to do all of this computation. I can see that a negative minus a negative minus a negative is going to give me something negative. That tells me that on this interval, my derivative is negative. So I'm going to mark that with little negative signs below here. Next, I'm going to look up this interval from 1 to 0, from 0 to 1. So on the interval from 0 to 1, again, I'm going to pick just sort of an exemplar point of 1/2. It's somewhere in between 0 and 1. What would happen if I plugged in 0 exactly? If I plugged in 0 exactly, we know what the derivative is going to be. It's going to be exactly equal to 0, which doesn't give us any information. So let's plug in 1/2 and see if we get something positive or negative. So that's going to be 12 times 1/2 cubed minus 48 times 1/2 squared plus 36 times 1/2. I can't look at these numbers and tell whether this value is positive or negative, so I'm going to go ahead and use my calculator to find this. This is 12 times 1/2 cubed minus 48 times 1/2 squared plus 36 times 1/2, just 1/2. That gives me a value of 7.5. And 7.5 is positive, so I know that my derivative is positive on this interval. I can write that as a positive, 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 positive. Now let's look at the next interval, the interval from 1 to 3. Again, I can choose any point I want in this interval, and I'm going to choose the point 2, just because it's easy. And we see that f prime of 2, rather than writing it all out, I'm just going to do it on my calculator. We see 12 times 2 to the third minus 48 times 2 squared plus 36 times 2 is negative 24. And that's negative. And our final interval for values of x bigger than 3, on this interval we see that f prime, I can pick any value I want. I'm going to pick 10 for no apparent reason, and plug that into our derivative function, and we see that we get 12 times 10 to the third minus 48 times 10 squared plus 36 times 10. We get a really big number. In this case, we actually get 7,560, which is clearly positive. So what does that mean? Positive, 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 positive. So what does this tell me about the behavior of our graph? Just looking at this number line here, we have a mental image now of what's going on. I'm going to overlay this simple x-axis with the number line. And we see that when x equals 0, our derivative is 0. We also found out that when x equals 0, we found the exact value of the point in this chart, that f of 0 is 0. F of 1 in this case is up at 5. Maybe I should put 1 over here. And that's 5. And then f of 3 we found was all the way down at negative 27. So my graph maybe isn't big enough to contain it. And now we also found that our derivative is negative until we hit 0, meaning it's sloping downwards. Then it's sloping upwards briefly until it slopes downwards again as it approaches x equals 3, at which point it slopes up again. So these points and the derivative being negative, positive is enough information for us to be able to sketch a graph of the function. And this is representative of 3 being down here at negative 27, right? So the final piece of information that we want to find, let me recall, we just found when it was increasing and decreasing, and this is if the derivative is negative, that means it's decreasing. If it's positive, it's increasing. If it's negative, it's decreasing. And if it's positive, it's increasing. So here's our summary of that information. That's number 3. And finally, we want to know what are all the local maxes and mins. And given all the work that we've done, we've already found them. We know that they are where our critical points are. And we see that we have a local min at x equals 0. We have a local max at x equals 1. And we have another local min at x equals 3. And this is our evaluation of this function. Let's verify our work by typing it into the calculator. Let's see what our calculator has to say. I'm going to clear this. Let's type in our function. Ooh, I don't know if you can read this very well, but this is the function 3x to the 4th minus 16x cubed plus 18x squared, and I'm going to say graph. And we're zoomed in pretty close, so maybe some of this behavior won't be captured, but you can get an idea by the way that it drew that it matches up pretty nicely with our little picture here, that it goes decreasing and it swoops up and decreases again and then increases at the end.